So I'm going to illustrate this process of calculating a chi-square by drawing a contingency table. A contingency table consists of rows and columns to represent the samples that you have taken and the behaviours that you are counting about those samples, or the categories that you're counting for them. So this is data from a survey that I've recently been working on, where I asked a number of men and women to answer some questions. All I'm going to be looking at for this purpose is response behaviours. So what I want to know is whether or not they responded to the survey or not. So it's a very, very simple level of analysis I'm offering here, and that's going to have consequences. At one point in particular, it's going to look like we've got the same answer in each box that we're working on. So bear with me whilst we get there. Now, when I started looking at this, the sample that I wanted to draw had to be drawn from a population that was predominantly female. In fact, 70% of the people who I was working with were female and only 30% were male. So, being a good researcher, I designed a recruitment strategy that would reflect that proportion. So I took the staff list of the company, I think there's about 300 people in it, and I decided a sample of 50 people would be sufficient to represent all the other variations and differences. And I then split the staff list into males and females, put the names into a hat, and drew out 70% of the 50 people as female. So that's 35. So I drew 35 female names out of the female hat. And I drew 15 male names out of the male hat. And that was the way in which I got to do it. So I then sent those people an email with a link to a questionnaire survey that was online and waited for them to answer. The answers came in at the rate of 28 responses, which I was quite pleased with. That's fairly high given this kind of exercise. Straight away I could see that I'd only got 22 non-responses. Now, because we're testing the hypothesis that there's a difference in behaviour, well, we're not testing that hypothesis, are we? We're testing the opposite. We're testing the hypothesis that there is no difference in behaviour between men and women in responding to surveys. And that's because we're going to test that hypothesis and hopefully show that it's false, so that we can reject that and have some evidence to support the idea that men and women behave differently in the way they respond to surveys. So to test that hypothesis, I have to have an idea of what I would expect if it were true. If it's true there's no difference, then I would expect 30% of those people to be male, because 30% of the population and the sample are male. And a simple way to do that, if you don't happen to know that your proportions break down like that, a very simple way to do it would be to say, let's make a proportion out of the number of people who fit into that group from the whole. So I would say take 15 out of 50 and then multiply it by the number of people who responded. And that gives me 8.4. So, all things being equal, I would expect 8.4 men to respond to the survey out of the 28 who actually did respond. And I would expect the same thing to work out. So now I've got that one item of data in there, because this is a very simple level of analysis, I can now work out that I would have then 19.6. Let's try that again. 19.6 people who would be female. And that's because 8.4 and 19.6 is 28. And similarly, I can see 8.4 plus 6.6 makes 15. And 19.6 plus 15.4 makes 35. And all I'm doing there is doing some subtractions using the column and row totals. You could do it by calculating proportions if you wanted to each time. But that's a very simple idea. So there's my expected values. If men and women don't behave in a particularly different way when it comes to responding to surveys, given that I only had a 30% male sample, I would expect 30% of the 28 people to reply to be male, and that would be 8.4 men. I know you can't have 0.4 of a man, but for the purposes of calculation, I'm leaving it at one decimal place for now. So, where do we actually get? What numbers did we find when we did the exercise? So I'm going to write in the actual responses that I got now. So I got 7 there, which means that I must have got 21 there because 7 and 21 is 28. And I must have got, of course, 8 here because 7 add 8 is 15. And I must have got 14 there because 21 add 14 is 35. So we can straight away see that there is a difference between what we expected and what we observed. The expected values, 8.4, 19.6, 15.4, 6.6. The observed values, 7 is less, 21 is more than what was expected, so on and so forth. I think we can see that there's a small variation between what we observed and what we expected. The question is it a big enough variation for us to conclude that the hypothesis that men and women don't behave differently is wrong? That's what we want to do. We want to throw that hypothesis out. Now, in order to know whether that variation in between expectation and observation is big enough, we have to actually work out what it is. And I think you can see straight away that because this table is so simplistic, that the difference between one set of observed and expected values is going to be replicated throughout. So the difference between 7 and 8.4, 7 take away 8.4, is minus 1.4. Here it's going to be 21 take away 19.6. That's going to be 1.4, plus 1.4, isn't it? So you can see that in each box we're going to have a difference of 1.4. That's going to be plus 1.4 there, this is going to be minus 1.4 here. Now if we added up all of those differences together, minus 1.4, plus 1.4, minus 1.4, plus 1.4, get to 0, and it would appear that there would be no differences. Well, clearly that's just a consequence of sign changing. So what we need to do is work out how big the change is and not worry too much about the direction. So what we're going to do is we're going to square that 1.4, because when you multiply two negative numbers together you get a positive, and when you multiply two positive numbers together you get a positive. So all the answers to the squares will be plus, and it will be plus 1.96. 1.96, 1.96, 1.96. So we've squared the difference between what we observed and what we expected in order to just measure the difference. We don't care what direction it went in. Now that tells us that there is this difference between these two values. Between what we observed and what we expected there's a difference of nearly 2. But is that 2 big or small? Well, it can only be big or small relative to something. So what is it going to be relative to? Well, because we made an expectation, is the difference that we see big or small relative to our expectation? The way we do that is by dividing it by our expectation. So we see 1.96 as a proportion of 8.4 of the expected value, or as a proportion of 19.6. So we can see that in this box here, in this box, the male responders box, 1.96, or 2, very nearly 2, is quite a sizable chunk of the expected value, compared to this box here, where it's roughly only a tenth the size of the expected value. Yeah, there's a variation there, isn't there, that's worth looking at. Is it worth getting excited yet? Do we really think we've seen a difference? Don't know. We'll have to do some more work. So what we do is we go through each box and we divide it by the expected value. 6.6 here and 15.4 here. When we've done that, what we've calculated is the difference between the expected and the observed as a proportion of the expected value. So we know how big of a change there is between observation and expectation here in this box. All we need to do now is add that difference up for each of the boxes. And that, when we do that, we come up with chi-square. That's how you calculate it. And chi-square for this set of data is 0.75 recurring, which I'm going to round to 0.76, because throughout this I've worked to 1 or 2 decimal places. So I've got to 0.76 as my answer there. Now, what does that mean? does that tell us that we've got a statistically significant difference in the behaviour of males and females? Or does it tell us that we're allowed to junk the hypothesis that there isn't a statistically significant difference in the behaviour of males to females? Can't tell yet, because we need to compare that response, that answer, to a critical table of values, or a table of critical values, sorry, so that we could work out what level of probability we'd have for saying that this difference was down to random chance factors alone. We'll have a look at that in a minute or two, but before we go on, I'm just going to summarise where we've got to at this point. What we've been doing, and I'm going to use the formula, the expression that we usually use for chi-square. There's the chi-square, the difference between observations and expectations. We squared that so that we would wind up with positive values all the way through. And we represented that difference as a proportion of what we expected. And then we added up all of those proportions for all of the data we've got. So to just explain, that last symbol I've just drawn there, that is a sigma, means the sum of all of. The E's and the O's are expectations and observations. You understand, the rest to be squares. You might see a slight difference between this formula and the ones that you might find in some statistics books, and that would be this. You might see sometimes that there would be an additional takeaway bit here, a little subtraction of 0.5, and then you go back to the square. And the reason for that, that thing, that gets called, that's Yates correction. Now Mr. Yates was concerned that the original chi-square statistic was calculated using this difference between observation and expectation was overestimating the significance. And he suggested that what we could do is slightly tweak the difference by this 0.5 value. So he said, let's get rid of that difference a little bit, let's reduce it slightly. So you see this Yates correction that looks like this in some versions of the calculation. Many statisticians say you don't need it. A truly cautious version of the calculation would of course include Yates correction and make a number of other stipulations as well. So just so you don't feel shortchanged on the whole thing, that's what that's about. Going back to our table then, we've calculated the difference between observation and expectation, we've expressed that as a proportion of our expectations, and we've summarised it to get the value of chi-square. What that means is something that will be revealed by comparison with a table of critical values, which we'll go on to do next.